Hi everyone, I am Cheng Zhao. Welcome our paper, Tracking Guided 4D Generation, Foundation Tracker Motion Priors for 3D Model Animation. Generating dynamic 4D objects from sparse inputs is difficult because it demands joint preservation of appearance and motion coherence across views and time, while suppressing artifacts and temporal drift. We hypothesize that the view discrepancy arises from supervision limited to pixel or latent space video diffusion losses, which lack explicitly temporally aware feature-level tracking guidance. We present Track 4D Gen, a two-stage framework that couples a multi-view video diffusion model with a foundation point tracker and a hybrid 4D Gaussian splatting reconstructor. The central idea is to explicitly inject tracker-derived motion priors into intermediate feature representations for both multi-view video generation and 4DGS reconstructor. We highlight our main contributions as follows. We introduce Track 4D Gen, a novel 4D generation framework that unifies diffusion generator, foundation point tracker, and 4DGS reconstructor, directly leveraging motion priors from foundation tracker to mitigate appearance drift via explicit temporal supervision. We propose a temporal-aware multi-view 4D generator combining video diffusion objectives with cross-frame dense point tracking/correspondence, enhancing the temporal consistency of diffusion feature representations. We develop a joint 4DGS reconstruction that learns motion field from hybrid representations by concatenating co-located diffusion features, carrying tracking priors, with hex-plane features for each spatiotemporal sample, yielding higher fidelity dynamics and appearance. We also introduce a 4D spherical harmonics modeling into 4DGS to improve color modeling. We construct a new high-quality 4D dataset, SketchFab28, to support object-centric 4D generation evaluation for further research. Given an off-the-shelf static 3D model, our aim is to animate it from a text prompt while using its multi-view static renderings as image condition. Track 4D Gen follows a two-stage pipeline. 1. We learn a multi-view video diffusion model that, conditioned on static multi-view images rendered from the 3D static object and the text description, synthesizes temporally coherent multi-view videos. 2. We learn 3D object animation via a 4DGS representation, taking the static 3D Gaussians as the canonical asset and estimating time-dependent motion fields from the generated multi-view videos. We leverage the motion prior from a foundation tracking model to strengthen both stages. Stage 1 establishes temporally consistent diffusion features for video generation via dense, correspondence-aware point tracking supervision. Stage 2 converts the synthesized multi-view videos into a dynamic 4D Gaussian representation, enriched by tracking-aware diffusion features. In Stage 1, we upgrade the 4D multi-view video generator with foundation keypoint tracking. We first use CoTracker 3 to obtain dense keypoint tracks on ground truth videos, and then locate their counterparts in the diffusion feature space of the generator. A correspondence tracking loss is utilized to align these feature-level matches across frames, providing explicit temporal supervision that suppresses appearance drift and improves cross-frame coherence. We seek the most stable feature space for point tracking in object-centric multi-view videos, i.e., features that reliably encode long-range temporal correspondences. We therefore probe the long-term tracking capability of UNet-based video diffusion models by evaluating block by block which features best support correspondence. Concretely, for a real video, we add slight noise, run the denoiser, extract layer-wise feature maps from every block, and compute tracks by cosine similarity nearest neighbor matching for a fixed set of query points on the first frame. This analysis yields a consistent finding. Features from the second spatiotemporal upsampling block in the decoder of UNet provide the strongest temporal correspondences, in particular those from temporal motion module in the spatiotemporal attention block. In Stage 2, we jointly optimize 4DGS with photometric losses and 4D-SDS driven by the multi-view videos from Stage 1. Unlike classic 4DGS pipelines that learn motion with only hex-plane features, we augment each 3D sample point along with time by concatenating hex-plane features with its co-located Stage 1 diffusion features. These diffusion features, trained under CoTracker 3 supervision, encode motion priors that strengthen point representations of dynamic geometry and appearance. Additionally, we introduce a 4D spherical harmonics modeling into 4DGS, which improves color modeling of 4D assets. Following Animate 3D, we compare our method against baselines along two aspects: multi-view video generation and 4D generation. We evaluate multi-view video generation and 4D generation on two datasets respectively, using standard metrics for each task. We provide video generation quantitative and qualitative comparisons for filtered diffusion 4D dataset in Table 1 left and Figure 5, and for Animate 3D dataset in Table 1 right and Figure 8. On Table 1 left, our Stage 1 model achieves the best results on all 5 metrics, indicating stronger image-to-video consistency, smoother motion, improved temporal stability, and higher aesthetic quality. On Table 1 right, our method ranks first on 4/5 metrics, while trailing in dynamic score. As shown in the visual comparisons in Figures 5 and 8, our method, leveraging foundation point tracking motion priors, produces more appearance-consistent frames, more natural motion, and sharp object boundaries. We provide 4D generation, quantitative and qualitative comparisons for SketchFab28 dataset in Table 2 left and Figure 9, and for Animate 3D dataset in Table 2 right and Figure 10. On Table 2 left, our Stage 2 model improves over the strongest baseline, Animate 3D, by clip-based semantic alignment metrics. On Table 2 right, it also yields clip-based semantic alignment metrics. These consistent gains in both object and frame-level alignment translate into a higher composite score, confirming better view time fidelity and semantic faithfulness. As shown in Figures 9 and 10, our method, leveraging diffusion features that encode tracking priors and 4DSH modeling, yields more accurate shapes, more realistic colors and lighting, and fewer artifacts. We assess the contribution of each module in Track 4D Gen via controlled ablations for multi-view video generation and 4D generation. Quantitative and qualitative results are reported in Table 4 left and Figure 6 for video generation, and in Table 4 right and Figure 7 for 4D generation. Removing correspondence/position supervision weakens multi-view temporal coherence in video generation, while dropping diffusion features or the 4DSH degrades appearance fidelity and increases artifacts in 4D generation, confirming each component's complementary benefit. We provide video demos visualizing multi-viewpoint tracking across different 4D objects, demonstrating the robust point tracking. We also provide comparison video demos of 4D asset generation between our method and the baselines, offering a more intuitive visualization of both appearance and motion quality. For the generated 4D assets, the early test cases, being more challenging, demonstrate that our approach significantly outperforms both baselines. In the later, comparatively simpler cases, our method still slightly surpasses Animate 3D and clearly outperforms DG4D. We present Track 4DGen, a two-stage framework that unifies multi-view video diffusion, point tracker, and 4DGS to animate arbitrary static 3D models. The core idea is to leverage foundation trackers as motion experts and inject their knowledge into both video generation and 4DGS. By injecting dense, feature-level point correspondences into the diffusion generator and 4DGS reconstructor, our approach imposes explicit correspondence-aware supervision that suppresses appearance drift and strengthens temporal coherence for 4D object generation. Thank you for your attention.